Folks, continuing along. Let's see. This time I'm going to get a stopwatch going so I don't talk for so long. Okay, so I'm picking up here, and we're going to talk about other types of UV-Vis spectroscopy. I'm going to let Daft Punk bring it in. I love this song. Trying to hit all the hits before the semester's over. All right. Getting pumped up. I think I got a lecture like this from now on when we go back to normal, whatever normal is going to be. Okay. One more round. All right. Okay, here we go. So let's get into more discussion of electronic spectroscopy and something that is hopefully familiar to all of you, UV-Vis spectroscopy, right? So we remember that this is a dispersion technique involving gratings and scanning one wavelength at a time. Resolution can typically be an issue in UV-Vis spectroscopy, since we're not using the Fourier transform. It can be typically harder to get better resolution. So resolution in UV-Vis spectroscopy is based entirely on your grating and your detector. Okay. So, but let's get into it. Let's get into the physics, the molecular physics. Okay. So we recall with our potential energy diagrams, right here we're looking at this whole entire potential energy well. We could think of as the ground electronic state. And we recognize, and so this is, sorry, fictitious molecule AB. Okay, just general molecule AB. Now, it's very easy for us to kind of recreate these types of potential energy diagrams for simple molecules, right? For larger, more complicated molecules, maybe a protein or maybe some type of highly conjugated dye molecule, we can still use this same idea, this potential energy well. Because remember, our electrons exist in these bound states, right? So this potential energy well is not just applicable to our small molecules. We can use this idea for all molecules, okay? So we start in this bound state, okay? This ground electronic state. And then what we have here, what I'm showing you in this diagram, here we have an excited bound state. And I'll just say bound, because we can see it has a minima, right? And you can also see there's various vibrational energy levels. Okay, so we'll say vibrational levels. We can also view, and of course I could also put vibrational levels in this ground state as well, right? And then here we have a repulsive state given by this R. And that repulsive state, right, we recall that's going to be an anti-bonding state that doesn't have a minima, okay? And so this is also kind of showing you another example if we had, let's say, two repulsive states, okay? So when we excite molecules, and I'm going to give us a more specific definition of this, we do what's called the vertical transition. And you guys have already kind of played with this with your exam, right? Which is pretty straightforward to calculate for simple molecules. And so that vertical transition gives us the initial absorption of a molecule, okay? And so if we try to imagine how does this now relate to what a UV-Vis spectrum will look like, that's what I have here on the right, okay? So here we can see we have potential energy on this y-axis. But now if we view this right here, okay, so I'm going to write spectrum. This is a spectrum tilted by 90 degrees, just rotated to be yx instead of xy. Okay, so if I rotated this spectrum by 90 degrees, right, it would look like my typical spectra, and I'll try to draw this picture exactly like the one that's drawn right here so you can see what's going on. Okay, so these spectra that we see are really like a map of the potential energy diagram, right? Which is kind of cool, okay? And so if you think about this now in this picture here, once again, we've got the ground electronic state and an upper lying excited state, okay? So I'm gonna note this as for our fictitious molecule, right? I'm gonna use that X terminology, noting that this is the ground state. And here you can actually see letter A, right? This is the A state, the next lying state. And then now what you can see here are the vibrational wave functions, okay? And really at this point, we recognize that those are the total wave functions, the total psi, because it's superimposed on the electronic levels, all right? And so we know that our molecule likes to exist in the ground electronic state, in the ground vibrational state, right? So right there is its sweet spot. And you can see when you look at that wave function, that's corresponding to the highest probability, right? That's where the wave function has got its highest peak. And so when we do this vertical transition, it's the most intensely observed line is going to be given from the best overlap, because the best overlap is going to create the largest dipole moment. So as I'm going up through this vertical transition, you can see for this particular molecule, right, there's really nice overlap at, let's call it the 4th vibrational level. There it is, okay? And now, because that's where the best overlap is given, and I mean, literally it's the best overlap because it's this vertical transition, right, where the bond length has stayed the same, and it's getting excited to another position where that bond length is the same, okay? We note, though, that this excited state does have a slightly different ground state bonding distance, right? You can see that on this scale, the internuclear distance is different for this excited state than it is for the ground state. But what we're looking for, right, what happens in spectroscopy, the most intense transition is given from the largest dipole moment, and the largest dipole moment will occur from this vertical transition wherever there is the best overlap, okay? And overlap is literally like where the wave function from the ground state is best represented by a wave function in an electronic state. So you can see it's literally going from peak to peak, okay? And so now what that means, this vertical transition line, that's going to give me the lambda max at that best overlapped area, okay, which is kind of cool. And so we also notice that this fictitious spectra that you're seeing, that there's a continuous absorption right here, and there's quantized lines on this side. And those quantized lines that we're seeing on this side are from the different vibrational levels. So now, as you can see, when we go, let's say if we go down this spectra, right, into the less intense transitions, you can see that's due to the fact that if we still do this vertical transition, perhaps let's say if we do the vertical transition to this level right here, there is a really, really small probability of finding the electron outside of this potential energy well. However, we can still find it there due to the albeit small but still possible ability for that electron to tunnel over to that vertical overlap, okay? And so correspondingly, what you can see, that's where the absorption is small. So absorption is small because there's really terrible overlap, right? And so as you can see, what happens as you go higher and higher, the overlap gets better and better and better owing to this Gaussian peak shape. So that's why our peaks are shaped like they are in UV-Vis spectroscopy, because we're literally seeing excitations from one energy level to the next, and what we're really looking for is where there's this best overlap, is what we call this. Okay, and so now, as you can see in this fictitious diagram, right, in this fictitious molecular spectra, at this point here, our Morse potential is done corresponding to that convergence limit. So at that point now, any excitations above that would just result in what we call photo fragments, right? So like shown right there, where the molecule actually is separated. We're still going to get absorption of light, but because now we're absorbing it past the quantized vibrational levels, right? We're outside of the well now at this point. We just get this nice, smooth, continuous absorption. Okay? So let's continue along.